Hello and welcome to Data Science in Industry vlog. Today I would like to continue the video where I would like to present you the typical steps in the data science project. Last time we discussed the first few steps, which is the first workshop with the customer where we pretend that we are a detective, data science detective. We discussed the topic related with data sources, and the next step related with exploratory data analysis. Now it's time for the bread and butter of a data scientist, which is data cleaning and data wrangling, and then the reward. Of course, the reward is the possibility to create an algorithm, maybe the machine learning algorithm, maybe the statistical algorithm, depends on the project. Maybe your own algorithm that you will create, you will publish, you will share it with the rest of the world. And then we can't wait to share the results with the world, right? So the final phase where we have to implement our AI algorithm somewhere. Maybe it will be a standalone algorithm with some simple graphical user interface, maybe a report or the scientific paper, or maybe it will be a part of the larger IT platform. So we have to add the API and discuss with software developers how to implement the algorithm within the larger structure. So now let's move forward to data cleaning and data wrangling. Very important steps that takes sometimes quite a lot of time. Sometimes, usually, they take a lot of time, but they are very crucial. Usually our data are very messy and we have to clean them. What kind of problems we can see in the data? For instance, one of the problems is the lack of uniqueness. We can have the same IDs for two different entries, for two different rows. Moreover, we can have the same entry, like here, the same name, coded in different ways. One is, let's say, Costa Rui, and here we can see the Rui Costa. This is, of course, the same guy, but if we will compare the name cell, we could, if the algorithm will compare the name cell, it can see that those are different entries, different values. We can have some incorrect values entered here, like 32nd day of a month here, right? Or the name of a country in the place where we should have name of a city. Moreover, we can have some missing values. Here we can see this missing value expressed in a set of nines. So the value 999999999 is the way how the IT word expressed infinity, or I don't know what to put here. So this for sure is something strange. We can have duplicates, like I already said before, and of course some typos, like here. This is very often if the human being have to put the value into the system. We can also have missing values, like here. Here we have a missing value, or the missing value can be expressed in a different way, depending on the system or depending on the human being that enters the information about the missing. In other words, if the human being don't know what to put inside, he can just put a dot, and we have to guess that it is the missing value. And of course, the world of things that can happen to us, that can happen to data, is infinitive. So we have to be very careful. It's good if we can watch the data, open it in Excel or in Python, in Jupyter, and just look at the data. And of course, we should write some scripts to catch all those suspicious elements of the data. Moreover, we could, well, especially in the healthcare sector, people like to use the colors in, let's say, Excel spreadsheets. And for instance, the red color of a cell might inform us that this value is bad, it has a bad quality, or some other information. And this is the real pain if we have Excels where the information is expressed by the color of a cell. But of course, this is also normal thing. We can explain to our scientific partner or business partner that the next time it's better to do it in different ways. But of course, we have to deal it somehow and check the color of a cell in order to create our own data set in our Python or our program. Now the question is, do we have a problem? What kind of problem do we have with this missing data? Is it missing at random or missing not at random problem? What does it mean? It's by saying missing at random. So the data are lost by accidents. Someone forgot to put the data, or there was a failure of a sensor, or the failure of an IT system that stores the values, and this is, or the personal error. This is done at random. So the simplest and recommended solution how to deal with this is to just get rid of this missing data. We can delete the rows or columns with missing data, but of course the condition here is that we can do it if the number of missing values or missing data is not high, it's relatively low. Then we can do it without losing too much information from the data. However, if you lose too many data, this way we should not delete rows or columns, but we should rather try to estimate the missing values. We can do it in, let's say, simple or hard way. In the simplest way, we can just use the linear interpolation to fill the missing values, to fill the gap, or we can use the last recorded value and repeat it, and this value in missing rows, in missing cells. But we have to be very careful, because such filling of the missing values can change the picture of the real analyzed phenomena. We are changing the distribution of particular parameter, and it can have an effect on the outcome of our project. If it's the crucial parameters, crucial values that are missing, we can try to do the hard way. So we can use more accurate methods to estimate those missing values. Like for example, we can try to use denoised autoencoders or nonlinear models in general to make models, yeah, that estimate those missing values based on other parameters. I think it's good if I can explain it this on particular example. This is, let's say, the flow from the water flow in one of CHP plants, and this is taken from a real life project. We saw that here we don't know what was the flow. for 10 hours we didn't have the information about the flow, and this is quite crucial parameter. So we tried to build a model. In this case it was an artificial neural network that tries to estimate the flow based on other parameters, based on heat demand, pressure and flow distribution within the network, flow and temperatures in other CHP plants, and here we have a result. So if we just use the linear interpolation, we will end up with something like this. The real flow was this one. I don't want to discuss why it was so strange in this time, but it was like this. However, our nonlinear model, the artificial neural network that tries to predict the flow, suggested that the flow should be like this, because the flow in other CHP plants has changed, the temperature of the water has changed, so it was enough to provide a relatively good estimation of the missing value. Good enough for the purpose of the project. On the other hand, we can have problems with missing values that are not random. But of course we have to check if they are exist not at random. Because if really there is some pattern of why the data is missing, this pattern is express some story behind why there is no data. So it's related with some story, with some explanation, and this is also the information that we can use because it tells us something about the phenomena. In such case, we should understand why we don't have data and double think what to do with this problem. Should we get rid of such data? Probably not. Of course, it depends, but probably not. Can we impute missing data? What can we do with this? So maybe another explanation is a real example. We had air quality sensor data and we tried to predict the air quality. So we have data from stations all around the stations that measures the air quality all around the US. And unfortunately, some air quality sensors in one of the US states were measured on top of a small mountain. And we didn't have sensor values for Sundays. Of course, at the beginning, we didn't know that there is some pattern, there is some story behind the missing data in this particular station. We just saw that, looking at the distribution, that there are missing data. What to do with them? Maybe we can get rid of them, but let's check if there is some pattern of missingness. Let's call it like this. And we saw that it is missing, that the values are missing on Sundays. And we checked where is this station, and we saw it's on top of a small hill. So we think, we don't know, but we can guess that there was no one who could read the sensor values on Sundays. So deleting all the values from Sundays would be a mistake. We can't get rid of Sundays from our training data. So what can we do? Any suggestions? Do you have an idea? Well, we could, for example, we can use the data from other stations that are nearby and try to, and based on the history of air quality values measured on top of the small hill from Monday to Saturday, we can try to estimate the value for Sunday, right? For instance, if the air quality is, let's say, better on top of the hill for the whole week, it will probably better on Sunday. But we don't have a value for Sunday, but we can take the value from other stations and correct this value for the fact that it's on top of the hill and the air quality should be better. All right, and now when we have the clean data, we can, or at least we believe we have a clean data, because usually not all the errors could be catched at the first at this step. Usually we have to come back to this step once in a while by looking on results of our algorithms. So the next step is data wrangling. Data wrangling refers to the process of cleaning, restructuring, and enriching the raw data so it can be used to train our algorithms. So our goal is to write a data processing pipeline here that will transform raw data into a data table that can be used by the machine learning algorithms, and of course to validate the data, to clean the data, maybe to generate new features. Usually the pipeline consists of, well, the data validation algorithm, so the data cleaning plus optionally data imputation. Then the next step in this pipeline is merging data sets. As you remember, we could have data set from different sources, the weather data, the data from the control system, data from asset management system. We need to all merge it together. Then transforms data into the form that is useful by our machine learning algorithms. Especially we should make something called tidying of the data. We would like to have this tidy format of the data. Then if we have too many dimensions, too many features, we can try to reduce those dimensions. This is especially important in the healthcare sector, but of course also in industry we can have too many dimensions, dimensions that are correlated with each other, and we can try to reduce it and operate in reduced dimensions. And then we can create also some artificial parameters that can be useful for our algorithm. Like, for example, if we are trying to predict the heat demand, we can try to create a feature called the temperature that is actually feel by the end users. So it's the mixture of temperature and nonlinear mixture of temperature and wind. We can try to, if we have some, I don't know, projects in power plants, we can try to estimate, for instance, the humidity of the fuel, of the coal. And those are some extra features that can be calculated and used in our algorithm. So what is this merging of data sets? As you can see here, we have, let's say, two sets. We can combine it into one data table. And what I understand by the tidy data. There is a strict definition of tidy data. In tidy data, each variable forms a column, and each observation forms a row. And this is a very useful format that helps us to play with machine learning algorithms. And let's take a look on tidying the data. Here we can see the data from the weather stations from one weather station in Mexico for 5 months in 2010. We can see it's messy. Here we have the ID of this weather station, the year, the month, the parameter that is measured, so minimal and maximum temperature, and the days from 1 to the end of the month. But it's messy. It has variables in individual columns like ID, year, and month. They are spread across columns, so those days from 1 to 31, and across rows, so this minimal and maximal temperature. We'll obviously have a missing data because not all months have 41 days. So there will be a problem for the month that has for months that have 30 days or 29 days. So we can try to make it more tidy, or to make it tidy in general. So instead of having those days as columns, we can, as separate columns, we can add a separate column called a day, where we can put the number of a day. We can also take those minimum and maximum temperatures as columns. So here we have values measured for a particular month, particular day. We see what is the maximum and minimum temperature. And of course, because there is just one station, weather station, we can try to get rid of this column. We can try to mix day, month, and a year. And here we have, let's say, a better format. However, if we would like to use month and days as separate columns, because, for instance, we would like to predict the weather, we can keep it like this. If we have too many input parameters or features, as we call them, or columns, if we look at the data table, and not enough observations, as you remember, each row is one observation in the tidy data, we might try to reduce we can try to reduce the number of features. For instance, if we have Sunday, Mondays, Tuesday, Wednesday, Thursdays, Fridays, and Saturdays in our data, we can try to have just two characteristics of a day. It's working day or weekend. Then there is a reduction. If we have a few, let's say, oxygen sensors, the data from the few oxygen sensors that measures, for instance, the oxygen in the combustion chamber, we can try to calculate the average oxygen level. We should also get rid of linear dependent features because it is not desired in regression to use the features that are linearly correlated. Maybe in the next videos I will explain why. Usually the physics, the control system, or human decisions, the operator decisions, applies those linear relations. So the produced megawatts, the parameter that is measured in the power plant, on the power boiler, can be, and it is, linearly correlated with the fuel flow because of the control system that controls the plant. If we want to generate more megawatts, we need to add more fuel. The linear correlation is obvious. The question is, if the value of this correlation is high enough to get rid of one of those parameters. It depends on the context. Because, of course, there are some fluctuations of fuel from fuel flow from this desired linear dependency between the produced megawatts and fuel flow. And if we have really a lot of data and we have no expert knowledge what to do with this, we can try to use for instance, the principal component analysis. The PCA is the linear transformation of data that converts a set of potentially linearly correlated variables into a set of values that are linearly uncorrelated, called principal components. In the simplest words, we try to look on the data from different angles. We try to manipulate do the linear transformations of our coordinate system, so the data that looks linearly correlated now are uncorrelated. And then we can work in the world, let's say, of those principal components, not the original values, but the principal components, where those principal components are orthogonal, are not correlated. Here is the example for a turbopump. The turbopump is expressed, the operation of turbopump is expressed by many parameters like the flow, pressure, current consumed by the engine, like the temperature of the oil, etc., etc. So there are many parameters that is measured on the pump. Some of them are correlated, like the engine load and the flow. So in order to have a picture of uncorrelated values, we can use the PCA. Here you can see the relation that is between the first principal component and the second principal component. So let's say, first axis of this linearly transformed coordinate system and the second axis. And by colors, you can see the values related with some anomalies, some faults, because we know about the faults. And here, for example, you can see let's say, a small island of data points, of values that are related with a particular type of a failure. We couldn't see this in the original coordinate system, but thanks to this PCA transformation, by looking at just the first two coordinates, first two principal components, we can see it. And sometimes it's easier to operate in this, let's say, artificial linearly transformed coordinate system with less features. Yeah, and this is the relation between, let's say, with the third and the fourth principal component. Here we can see another island, another set of data related with a different fault. On the end, we can try to create some artificial parameters that can be useful. For instance, the information about holidays, if we are trying to predict the load, the heat demand, the electricity demand, the demand for gas, or gas or electricity prices. The information about the holidays is important, and of course we can try to create it based on the information about the country for which we are doing such a prediction. We can try to introduce lagged parameters, the parameters that are shifted in time into our data, to give the possibility to our algorithm to catch the process dynamics. We can try to estimate the fuel calorific value by looking at if it's the power plant, we can look on how much megawatts we are producing and what is the fuel flow. And based on this, we can try to estimate the fuel calorific value. We can also try to use inputs from different models, outputs from different models as an input to our algorithm. For instance, if we, in case of the district heating network, where we were predicting the heat demand for each particular substation, each particular heat exchanger in the building, we were using as an input the output from the artificial neural network that predicts the heat load for the whole network. So this other model gave us the context, that gave us some baseline, and the second model, the second algorithm, calculates only the deviation from this baseline. Now we are moving to the reward step, step 5. So step where we will try to create our own algorithms. And of course, we have to decide if it's the statistical algorithm or machine learning, AI algorithm. So usually if we operate in the healthcare sector, because we are doing a lot of projects for the healthcare sector, the statistics here are important. We would like to see the proofs of some relations that we can see in the data. In case of the data science in industry projects, we rather try to see the patterns that are within the data in order to predict future outcomes, in order to create digital twins, predictive models. So here the machine learning algorithms are more useful. Okay, and what are the typical machine learning projects? We can do the supervised learning, or we can do unsupervised learning. Of course, we can also do the reinforcement learning, but I will not focus on this in this presentation. So supervised learning, unsupervised learning, or reinforcement learning, but in case of supervised learning, it's the classification or regression task. In case of unsupervised learning, it's the clustering. So in supervised learning, we have the input data as well as output data. We know what is that. We try to find a link between this input data and the output data. In case of some pattern, some model, right? In case of an unsupervised learning, we only have some values. Maybe those values are related with some device, with some process, with some bigger industrial system, but we have values from sensors, values inputted by the user, values from different IT systems. And we are trying to find groups of similar patterns that exist in the data. So we are trying to create some clusters that are characterized by the fact that data within the clusters within one cluster are similar according to some measures of the similarities that we will define. So here is another picture of this. In case of unsupervised learning, or in case of clustering, we would like to find such clusters. We can say those are two clusters. And those are, for example, anomalies. This way we can try to find the anomalies that are related with the operation of some devices or industrial processes. But generally, we would like to split the data into clusters, into groups. We don't know a priori that, for instance, this group, this is, let's say, a class 1 group, or the group called, high unit load, and this group is called low unit load, or this is good operation, this is bad operation. We don't know this. We have just those values. In case of supervised learning, we not only have values, but we have some labels in case of classification task, for instance. Yeah? So we know that, or not labels, but values of the output in case of regression models. Here is the classification task. So we can see that we have values, those dots. Maybe this is pressure and this is temperature. Why not? Well, let's pretend. And we know that this is, let's say, optimal operation, this is not optimal operation, or this is operation during the summertime, this is the operation during the winter time. So we have some labels. Someone tells us about this. Or we could link those values, those sets of temperatures and pressure, with some labels. And our goal is to find a model, is to find a border between those classes, is to create a classifier that will tell what is the class of a new set of data. If we get a new set of pressure and temperature, we'll be able to tell that this is a winter operation or this is summer operation. This is a good operation, this is bad operation. This is fault, this is normal operation. So our classifier will try, based on the most recent data, will try to predict the class of this data. If it's the classification problem. If it's the regression problem, it will try to tell us what is the value of our output, of our parameter that we would like to estimate. For instance, if we have this, temperature and pressure, we might want to predict the flow in the district heating network. So in case of regression, linear or non-linear, we try to guess, we try to predict the value based on input data. In case of classification, we try to find a model, a function that splits the data into classes. And based on this model, we try to estimate the class, the label, based, for instance, for this particular pressure, for this particular temperature, this is optimal operation. So once again, the regression tried to guess the value, the number, try to find a model between the input parameters and the output. So the regression model will tell us that tomorrow there will be 84 Fahrenheit outside. But the classification model will tell us, will it be hot or cold tomorrow, right? I hope that you got a feeling of what is the difference between regression and classification, and generally between supervised and unsupervised learning. Of course, we'll talk a lot about those topics later on in more details in the next videos. But now I would like to go to the final phase, the presentation of our results. So we are very proud of our algorithm. We have checked it on the historical data that they are actually operating properly. Maybe we did some first implementation, some POC that proves that those algorithms are working properly. Now it's time to do the deployment. So one of the way we can share our results with the world is to write a scientific article, make a report, give the presentation or the speech on the conference, right? Another way, of course, it all depends on the project. If our algorithms are sending optimal decisions to the control system, we have to make a program that will allow us to communicate with the control system of a plant or of the factory. So we also have to make some changes in the control system just to be sure that the communication between the control system and the AI algorithm is safe. Probably we'll have to do some modifications of the graphical user interface of the operator graphics within the control system, like it is presented here. This is one of the power plants. And this will be a topic of a different video, how to communicate AI methods with the control system. Here you can see that every 10 minutes new settings are sent, new set points are sent to the control system, set points that are calculated by the AI method, which changes the shape of the fireball within a big power boiler in one of the power plants. Thanks to this, the efficiency of the combustion process increases and the emissions of NOx or CO, so all those harmful gases, is decreasing. All right, and also the AI method can be part of the larger system. Here you can see, for instance, the system that predicts the heat demand for the district heating network in Warsaw and optimizes its operation. It gives support for dispatchers how to operate this network in the optimal way. So this is a big IT system and the AI method is part of the system. So for instance, here's the graphical user interface that presents the real heat demand here in black and predicted heat demand for a few days ahead here in red. Okay, so I hope that now you have a feeling of what are the typical steps in such a project. If you have any questions, if you would like to comment this video, it would be great to hear. Did you like it? Do you agree with me? Do you have different experience? Here I wanted to share all my experience from projects that I did working in transition technology science together with my team. So I hope you will like it. But if you dislike it, also please leave a comment. Thank you.